Okay, we are going to start chapter 9 today, and we are going to have an exam on Thursday. It's not covering chapter 9, but we have to proceed with our lecture. And your exam will be posted tomorrow afternoon, and you can do them on Thursday. And Thursday, we do not have lecture. Yeah, and that will be all. So, chapter 9 is about the center of mass and linear momentum. We actually talked about the momentum in our lab last Friday. Wait, yeah, last Friday. Momentum is actually mass times velocity. Before we do linear momentum, we are going to talk about the center of mass. So, what is center of mass? See here, if you take a look at the motion of this bar, I think it's a baseball bat, you are going to see the motion of rotating object can be very complicated. So like here, and also flipping, like here, flipping this baseball bat into the air. But we have a special point. If you see this little point here, the point in the middle, there is this special point on this object for which the motion is simple. So if you do not take other points, if you take this point here, you will see the motion looks like a parabola. So here on the center, you see this dashed line here, it's the purple line, is a parabola. So the center of mass of the bat chases out a parabola, just as toast a ball does. So there are a lot of other things. If you toss a baseball, not a baseball, if you toss a football like this, and if you find the center of mass, the center of mass will also chase out an parabola, but it's rotating. So all other points rotate about this point, and this point is what we call center of mass. Okay. So the center of mass COM of a system. So if you say COM, that's not a com, okay? In physics, that's the center of mass. So the center of mass of a system of particles, we have a definition here. The center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated there. And also, all external forces were applied there. So we have two conditions. It's all of the system's mass were concentrated on that specific point, and all central forces were applied there. So if you have two masses, see, if we have M1 here and then M2 here, how to calculate where is the center of mass? So if you have a mass look like this, the center of mass will be somewhere in the middle, okay? So if this is 0 and this is D, what we should do is we use M1 times the coordinate of x1 plus M2 times the coordinate of x2, which is the D here, divided by M1 plus M2. So center of mass is also like measuring the average location of the masses, okay? So it gives you the average location of the mass distribution. So we have M1, X1, M2, X2. In this case, we have X1 equals to 0, and then X2 equals to D, and then divided by M1 plus M2. So we are going to see the center of mass will be some point here, COM, and equals to CM2 divided by M1 plus M2. So this is a very specific case when we have M1 is at the origin and M2 is at the location D. And for a very general calculation, so if we have particles, let's say M1 here, M2 here, and M3 here, and keep on going, okay? And this guy here gives you x1, and this guy here, the coordinate is x2, and then of course we have x3 and keep on going. So how to calculate the center of mass? The center of mass actually will be equal to m1 x1 plus m2 x2 plus m3 x3, and if you have more, you are going to add more, and then divided by m1 plus m2 plus m3, and keep on going. So plus all the masses you have in the system. Okay. So here, and the center of mass, you have two masses here. The center of mass is in the same location, regardless of the coordinate system used. So if we have a mass 1 and a mass 2 here, we find the COM here. And if we have a new coordinate system, so the origin is here, the COM is still between the two masses, and it's here, okay? So the location of the center of mass with regard to the location of the masses will be the same, okay? So it's a property of the particles, not the coordinate. So if the coordinate changes, the center of mass, the location of the center of mass with respect to the masses will be the same, okay? So shifting the axis does not change the relative position. So this is the relative position of the COM. And then we have this calculation here, okay? So for many particles, we can generalize the equation. We have this, and then we have this and this. So M1 plus M2. So if we have Mn, n particles, M1 plus M2 plus M3 all the way to Mn, and multiply by the location here for each single particle, divided by the total mass, you can get COM, okay? Usually we are not going to have a lot of particles in the system to do your calculation, but remember the equation. It's mass times the location of the mass plus the mass times of the location of the mass. So you are going to add the masses times the location of the mass, and then divided by the total mass. And in 3 dimension, we are going to have x calculated this way, y calculated this way, z calculated this way. So what is this? This is the same as m1 y1 plus m2 y2, and keep on going, okay? And then divided by total m. And also your z will be the same. Find the z coordinate for the masses and divided by the total m. And if you want to find, so here, if we want to write the center of mass in vector form, so we have MIRI. So RI represents the position of each mass. Okay. And for solid bodies, we take the limit of an infinite sum of infinite small particles, which we got integration. So here, if you take a look at this, if we have a continuous distribution for any solid, what we like, if we have a continuous distribution, I do not need to tell you this. So this guy here, because n goes to infinity. So that's why this little guy here, the summation here will become an integration. So that's why we have this guy here. So if you look at it like this, it's x t m. Okay, so for each little mass, multiply by its location and do an integration over the whole body. So that's why we have this for x direction, this for y direction. So the mass, the little piece, times the position of the little piece, do the integration over the whole mass, whole object, and then divided by the total mass. And also the y direction, z direction will be the same. So m is the mass of the object. And also here, if we limit our object to be uniform with density rho, so if this is our density, then this little dm, you can write it as rho dv, right? If it's a uniform object. So rho dv, and then this is the big M is rho v, okay? So it's x rho dv and rho v, the rho get crossed out. And you are going to, rho is the density, and you are going to get 1 over the volume, x dv, and for y direction, z direction, you have the same. And you can bypass one or more of these integrals if the object has symmetry. So what does this mean, object have symmetry? For example, if you know, let's say if you know a rectangle, okay, and it's uniform, So no, we know the center of mass should be somewhere in the middle because it's symmetric about the xy plane. So this center of mass must lay on xy plane. Must lay on the center, so it should be like this. So this is the center of mass. So if this is not very clear, I can give you another example. So for example, if we have a heart, okay, so we know this heart is symmetric about this line here, right? So the center of mass must be on this line. And when you do integration, you do not have to do, so this one here, we know if this is our x, this is our y, and this is our z. Okay, so we know it lies on this line here, which is, so what is this line here? This line is your, this is our z-axis. So this line is our x equals to 0 and then y equals to 0. Okay, so we know it lies on here because it's symmetric about z-axis. So the center of mass lies at a point of symmetry, okay? So if we have a line of symmetry, the center of mass must lie on the line. If we have a point of symmetry, then the center of mass lies on the point. So it lies on the line or plane of symmetry if there's one. And it needed not to be on the object. So consider a doorknob. So if you have a doorknob, the center of mass, so you have a hole here. The center of mass is actually in the center, okay? Because you have symmetry. I'm not going to, this is not a very good line because you have symmetry like this, you have symmetry like this. So this is the center, and the center, you must have your center of mass lies on the line of symmetry. Okay. So we can take a look at this checkpoint. It reviews the definition of COM. See this figure? The figure shows a uniform square plate from which 4 identical squares are at the corners. And then the corners are removed. Okay, so 4 identical squares at the corners will be removed. So A, where is the center of mass of the plane originally? So originally should be here, right? Because it's symmetric about x and symmetric about y. So where it is after the removal of square 1, and then square 1 and 2, and square 1 and 3, and the square and 1, 2, 3, and all squares. So answer in terms of quadrant. Okay. So if you are going to remove the first one, so I'm going to take a look at this first one. And after that, what you are going to see is you are going to see the symmetry. So here, we are going to draw a line of symmetry here. So we know if you remove 1, right, we know this object will be, so this plane will be, or this plate will be symmetric about this line. So this line here is actually y equals to negative x because it goes through the first, actually the second and the fourth quadrant, and it goes through the origin. So this is y equals negative x, but it should be on this side more or this side more. It should be in the fourth quadrant because you are taking a little mass here, then the center of mass should be towards the mass is more concentrated. So that's why it should be somewhere here. So that's why for B, remove 1, you are going to get a Q4 and along the y equals to negative x-axis. And then we can take 1, 2, 3. Let's take a look at remove 1 and 2. And you can do the rest by yourself. It's very simple. So if we remove 1 and 2, what will happen is this object, this plane, will be symmetric about this line, which is our this line here, okay, which is our y-axis. But the center of mass should be towards the region where we have more, where the mass is more concentrated. So that's why it should be somewhere here. So that's why it's along y-axis and actually along the negative y-axis, okay? So that is better. Okay, along the negative y-axis, you can do D, E, F, and by yourself. E is very similar to B, and D, it's you are removing 1 and 3. So 1 and 3 is the object is symmetric here, right? 1 and 3 is symmetric about this line here, and the center of mass, because it's removed symmetric, so the center of mass should be here. And it's also, if you remove, let me see, let me redraw it, okay. So if you are going to remove 1 and 3, you can find the symmetric lines. 1 and 3, they are removed. So this object is symmetric about this line here, and it's also symmetric about this line here. So these two lines intercept, and then you should have your center of mass here. So it's at the origin. So try E and F by yourself. It's very simple. As long as you can find the symmetry, you will be able to solve the problem. Okay? And we can also do subtracting. If you want to find the center of mass for this little thing here, for this shape, it's find the COM of a disk with another disk taken out of it. So how to do that? If you want to find the center of mass, it should be equal to m1x1 plus m2x2 and keep on going divided by the total m. So for here, because we are taking out this guy here, we should do m1x1. So if this whole thing, this bigger circle is m1. If we're taking out this small little circle, we should do minus m2x2. Because this part is blank, so we should do negative, okay? And then divided by m1, actually plus negative m2, so you should do minus m2, okay? And then you can find the center of mass for this. It's because these two, so if you do this guy and if you do this guy add together, you are going to get the composite plate, C equals to S plus P. Okay. So here, we can derive this because what do we have? If we have disk S, so this is our disk S. This is S, this is P. Okay, plate S, plate P, because MS XS plus MP XP divided by MS plus MP will be equal to the origin here. Because this is the origin here. And then you can find out where is your XS. XS is this little distance here, R, and you can find out where is your XP, because this whole thing here is the total big M. This is big M, M1. You can use this, is easier, but you can also use this. It's the same thing. Okay? So you can also get your XP here. So here, find the center of mass for each individual disk. Find the COM for two individual center of masses, treating the cutout as having negative mass, so having negative mass. And also, you can either use this way or use this way, but you are going to get the same thing. If you are going to view a takeout, you can, if you are going to view if there is a cutout from the plate, you can view it as a negative mass. Okay, so plus becomes minus. Okay, and then we are going to take a look at Newton's second law for a system of particles. And there will be internal forces between each of the particle. So we take a look at this. The center of mass motion continues unaffected by forces internal to the system. So what is force internal? So if we have M1, we have M2. So there might be forces between M1 and M2. So those are what we call internal forces. But if you have an out force that is applied to the system, so it's not between the masses, it's an external force. It's an external force out of the system, then this force will change the acceleration. So that's why here, motion of a system of a center of mass, because you can say these two, if they are internal forces, F12 and F21, they are oppositely directed, right? So the effect will cancel out. Okay, so the F net, if you do F net, the internal forces will be canceled out. So that's why here F net will be the sum of all external forces. So it's from the outside. And apply Newton's second law and to the center of mass, then F net will be equal to MACOM. So this is the acceleration of the center of mass. And the x direction, y direction, and z direction, they are the same. So m is the total constant mass of a closed system, and the ACOM is the center of mass acceleration. Okay, so F net, if you want to calculate the effect of a system of particle, what you should do here is you should find out where is the center of mass, and the force is actually acting on the center of mass. And the acceleration can be calculated for the center of mass. Okay. So here, we are going to using the center of mass motion equation. So here we have a Billard collision. So forces are only internal. So for the system, your force equals to 0, acceleration equals to 0. And for the baseball bat, before you see the baseball bat before, is this little guy here, the baseball bat. What is the acceleration? So if you take the acceleration of the center of mass, it's actually doing free fall. So that's why acceleration will be equal to g. So center of mass follows the gravitational trajectory. And we have, oh, here we should have a equals to negative g, okay, because it's free fall. And if we have an exploding rocket, explosion forces are internal. So only the gravitational force acts on the system, and the center of mass follows the gravitational trajectory as long as air resistance can be ignored for the fragment. Okay, so you see the explosion, but the center of mass is like somewhere here, and the center of mass will follow the parabola trajectory. It's a gravitational trajectory. Okay, it's a parabola. Okay, now let's take a look at this example here. So two skaters on a frictionless ice hold the opposite ends of a pole of negligible mass. An axis runs along it with the origin at the center of mass of the two skater system. So one skater Fred weighs twice as much as another one, Ethan. So where do the skaters meet? If A, Fred pulls hand over hand along the pole so as to draw himself to Ethan, and Ethan pulls hand over hand to draw herself to Fred, and C, both skaters pull hand over hand. So what does this mean? We are going to have two skaters. So it's like this. Pole. Okay, so they are doing this. So these three objects are in a system. Okay, So here, if you notice, this is a frictionless surface. So the forces between the skaters and the pole is internal. So we do not have external forces. That's why you can see here. The system consists of Fred, Ethan, and the pole, and all forces are internal. So there is no external forces. If we have the COM here, the COM will stay here, right? The center of mass will not change. So therefore, the center of mass will remain in the same place because we do not have external forces. Then we do not have, so we do not have external forces. And then the center of mass will not change. And since the origin is the center of mass, the origin is the center of mass, they will meet at the origin in all three cases. Okay? So see here, if you try to pull, they are going to meet here at COM. Okay. So that's why it doesn't matter which one has a heavy mass. Because if this guy here, this is Fred, and this is Ethan, this guy here is twice heavy as this, then our COM should be more towards Fred. But no external forces. If they have to meet, they are going to meet in the middle here. It's not in the middle, it's going to meet at COM. So this is that. And then once we know the definition of COM, we are going to talk about momentum. Okay, here. The linear momentum is defined as P equals to mv. We talked about this before. So momentum points in the same direction as the velocity, so it's a vector, but it points in the same direction as v. And can only be changed by a net external forces. The internal forces for the system will not change the momentum of the object, okay? So the time rate of change of momentum of a particle is equal to the net force acting on the particle, and is in the direction of that force. So basically, our net force will be equal to the change of momentum divided by the time, okay, the time rate of change. So force will be equal to delta T over delta T. Why is that? It's because this momentum will be equal to m delta V over delta T. What is delta V over delta T? Velocity over changing time, that's actually your mass times acceleration. So that's why our force will be equal to the changing rate of your momentum. You can also write it this way. We can write Newton's second law in terms of momentum is F. The net force will be equal to the change of momentum. So we don't write it as ma anymore. You can write it as the change rate of momentum. So we take a look at the checkpoint. The figure, so this figure gives the magnitude of P of the linear momentum versus time for a particle moving along an axis. A force directed along the axis acts on the particle, okay? So we have P and we have T. So rank the four regions indicated along according to the magnitude of the force. Grade is the first. And in which region the particle is the particle slowing. So what does this mean? It's our F net will be equal to dp over dt. And you are going to rank the magnitude. So you are going to do an absolute value. So this is actually calculate dp over dt. This is actually the slope of the line. So see this guy here, so slope 2, S2, I'm going to write here, S2 is 0, and S4 is also 0 because they are horizontal. And for 1 and 3, actually 1 goes faster than 3 because 3 is less steep than 1. So S1 should be bigger than S3 and should be bigger than S2 equals to S4 equals to 0. So slope, this one is increasing faster and this one here, it's decreasing slower. So for magnitude, S1 is bigger than S3. I'm going to do this. So that's why for the magnitude, we rank it is 1, 3, 2, 4. Okay. And the other thing you also notice, it's S3 is actually going this direction. This direction, our S3 is actually negative. Right? So negative, what does negative mean? Negative means M delta V over delta T. See here, this is negative. Negative means the future velocity is less than the present velocity, so that our changing v is negative. Changing v is negative, then our velocity is decreasing. Decreasing, then the particle is slowing down. So that's why our region 3, the particle slows down. Using the definition here, is S will be equal to dp over dt. And we can sum the momenta for a system of particles to find the p total. Okay, so p is equal, it equals to mass times the center of mass velocity of the system. So this is linear momentum for a system of particles. If you have a single particle, p equals to mv. Okay, if you have a system of particle, then it equals to m1, so do it like this. And keep on going. And this whole thing here, you can write it as total mass times the center of mass velocity, okay? The linear momentum of a system of particle is equal to the product of the total mass of the system and the velocity of the center of mass. Okay, so center of mass for a system of particle is very important because we have to use it to analyze the momentum. The center of mass velocity determines the momentum of the object. Okay? And then we can take in, so this one here, taking the time derivative, we write the Newton's second law as this. We derived this before for a system of particle. And the net external force on a system changes linear momentum. So this guy here changes P. Without net external force, the total linear momentum of a system of particle cannot change. So if F net equals to 0, then your momentum is conserved. It will not change, then momentum is conserved. And then we have collision and impulse, and we are going to see the conservation of momentum. So here, first thing we are going to learn is impulse. So in a collision, momentum of a particle can change. So what does collision means? If these two objects bumps into each other. So maybe this guy have initial velocity v1 initial, and after the collision, so then this guy may move to the opposite direction and you are going to have v1 final. So from initial to final, that tells you momentum changes. The reason we have momentum change is during the bend process, the collision process, there will be force applied by, let's label this guy M2 on M1, because think about what happens during collision is the forces applied between the two objects. Okay, so the forces apply and we do force. So here during the collision, you may have a force applied. So this may be the initial contact. We do not have any force, and yeah, we have the picture later. And then when they are collide, here you are going to have a maximal force, and when the object leaves each other, the force will decrease. So here, if we do force as a function of time, we may get a curve look like this, and the area under the curve is our impulse. And this impulse is F dt. Say F dt. What is F dt? F dt is actually this. So take a look at F dt. F dt will be equal to dp. So do an integration. You are going to have this is change in p. So F dt, the impulse will be equal to the change of momentum. So this is J equal to F dt will be equal to delta p. So J will be equal to F dt. So this means that the applied impulse equal to the change of momentum. Okay, F dt equals to change of momentum. And this is what we call linear momentum impulse theory, or sometimes we call it impulse and momentum theorem. Okay. And this equation can be written component by component like all other equations. So you may have Jx equals to delta Px, Jy. So what does this mean? And then Jy equals to delta Py, and then Jz equals to delta, this is y. Jz equals to delta Pz. Keep on going. And you can see here, the impulse in the collision is equal to the area under the curve. So this is initial contact, and this is the end of the contact between the two objects. And here, if we can find the average force during the collision, you can kind of like put this little part. Yeah, I'm drawing this too big. Okay. So you can kind of like put this little part here, put this little part here to fill in the blank. And then you may be able to get an average force. So this is average force. And the area of this blue rectangle is the same as the area of the purple curve. Okay. So these two are the same. So here we are integrating. We only need to know the area under the force curve, and the average force gives the same area under the curve. Okay, so the two area will be the same. So during this process, it's the same as we have average force acting on the particle for this amount of time. So impulse will be equal to F average times delta T. Okay. Okay, so here we can take a look at this conceptual example. Oh my gosh. Wow, he cannot open his suit and lands in snow. Okay, it is likely that he lands in snow. So take a look at this problem, okay? Paratrooper whose suit fails to open and lands in snow. He is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter than, and the collision is lethal. So does the presence of snow increase, decrease, or leave unchanged the value of A, the paratrooper's change in momentum, B, the impulse stopping the paratrooper, and then the force stopping the paratrooper? It will increase the, so what does this mean? It increase the time, right? So see here, it's F delta T will be equal to delta P. Okay, the change in momentum will be the same because it will stop. Okay? So from initial velocity, V initial to stop to V final, which is 0. So the velocity change will be the same. Momentum will be the same, okay? in different situation, and also impulse will be the same. What is different is the stopping time. So delta t is bigger for snow. So that's why your force, if t is big, then your force is small. So that's why your force is decreased. And that's why usually we have, if you have car and your car is usually have a bumper in the front, what the bumper do to your car during collision? The bumper will increase the collision time so that it decrease the forces and do less damage to your car. Okay. And for a steady stream of m particles, each undergoes a momentum change delta p. So here we have a series of particles, then the impulse will be equal to negative n delta p. Usually we are not going to have this. Okay, we can take a look at the physics behind it. Is the average, see here, so if the particles undergoes change of momentum delta p, so that means your initial, so here with the negative sign means the final minus initial, you have the you should have, yeah, why we have this negative? Yeah, our impulse will be equal to the change of momentum. Yeah, we don't need the negative sign. Oh, I see. Why we have the negative sign? If the particle is delta V is V final minus V initial. And then if our final is 0, our initial will be negative V. Okay, I see. So m particle, this is our change of momentum, and then this is our, then yeah, we can ignore the negative sign here. It's the force equals to the change of momentum. We can just write it as n delta p. We don't need a negative sign. If the velocity change is negative, final minus initial is negative, then we can put it in. Yeah, it might be different from the initial velocity, but it's okay. Looking for a little bit. Why we need this negative sign? Also momentum change delta p. V goes in. V goes in. If we have m particle, if we write its final minus initial, then hmm. Yeah, delta p. We shouldn't have, like, the negative sign actually doesn't make sense here. I have that. Yeah, J equals to delta P equals to M delta P. Why we have the negative sign? I don't think we have the negative sign here. We should be positive, but I have to double check why we have the negative. Don't think we should have it. It's F will be F average times delta P will be delta T will be equal to change of momentum. I will double check on this. For now, I don't think we are going to use this anywhere, but I'll double check this with you guys and give you the right equation later. I don't think we need a negative sign here because from the definition of force and impulse and also momentum, okay? But this delta V here will be final minus initial. Anyway, so let's take a look at this checkpoint here. The figure shows an overhead view of a ball bouncing from a vertical wall without any change in speed. So consider the change delta P in the ball linear momentum. So is delta P x negative, positive, or zero? And is delta y positive, negative, or zero? And what is the direction of your delta P? So we are going to define this guy going up, right? This guy going up. Going up is our positive x-axis. So the V here is the same as the V here. If you take a look at your x direction, so V initial x will be equal to V0 sine, this is x, okay, theta. And the V final x is also, so this is V initial sine theta. So delta Px will be equal to M V final x minus V initial x, M delta V. This is M delta Vx, okay? So this guy here, V initial 0 sine, V initial 0 sine, this is 0. So no change for x. But for y, V initial y will be equal to, it's going down. So it's negative V initial, and this should be cosine theta, okay? The adjacent side. And V final y will be equal to negative. It's not negative anymore because it goes up, so it's positive with 0 cosine theta. And then your delta Vy will be equal to 2V0 cosine theta. Use this minus this. And then that's why you are going to multiply by the mass. So you are going to get 2m V0 cosine theta. So it's positive and it's along the positive y-axis. Okay. So that is that. And then we have conservation of momentum. This is what we did for the two ball collision in our previous lab. I think it's a lab on, I forgot, it's the lab on Friday, I think. Okay, so here for an impulse of 0, we find T is constant, which says that if no net external force acting on the system of particle, the total linear momentum P will not change. Okay, so momentum will not change. So this is what we call the law of conservation of linear momentum. Okay. So we have to check the components of the net external force to know if you should apply this. So if the component of the net external force on a closed system is 0 along an axis, then the component of linear momentum of the system along that axis cannot change. So some external force maybe only act on y direction, then your x direction momentum will not change. Okay, so this is conservation of linear momentum. And the internal force cannot change the momenta of parts of the system, but the internal force can change some of the momentum in the system, but cannot change the total momentum of the system. Okay, so it cannot change the linear momentum of the entire system. And do not confuse momentum with energy. Okay, here I want to remind you kinetic energy. What is that? It's 1/2. And the momentum. And one is vector, the other one is scalar. Okay. And then we take a look at this conceptual example. An initially stationary device lying on a frictionless floor explodes into two pieces, which then slide across the floor, one of them in the positive x direction. So what is the sum of the momenta of the two pieces after explosion? The initial is 0, so P initial will be equal to P final, which equals to a constant, so it should be 0. So can the second piece move at an angle to x-axis? No, because our F net goes to 0, okay? The second piece should move in the negative x direction. Okay, what is the direction of the momentum for the second piece? Because it equals to 0, m1 v1 plus m2 v2, the two pieces. So here you are going to get m1 v1 equals to negative m2 v2. So v1 is positive, and then v2 should be negative, so that m1 v1 is negative m2 v2. Okay, and then we have a momentum and a kinetic energy in collisions. We have different type of collision. We have elastic collision. So elastic collision, what we have is the total kinetic energy is unchanged. So this is elastic collision. So elastic collision is a very useful approximation for common situation, but in real collision, some energy is always transferred. Okay, usually if you take a look at the billiard ball, the head-on collisions, we can consider them to be elastic. And we also have this is the most general case in our daily life is inelastic collision. So some energy is transferred. So you may have loss of kinetic energy. You may have gain of kinetic energy like explosion, but the momentum for the different cases will be the same, okay? And then we also have complete inelastic collision. Is the objects stick together after the collision, and we have the greatest loss of kinetic energy, okay? So kinetic energy is conserved, then is elastic. Not conserved, then is inelastic. And if objects stay together after collision, then we call it completely inelastic. And we have a very easy case here for one dimension. Inelastic collision is M1. So these are the two masses, M1, M2. Yes. We have M1, we have M2. You can have M1, M2 moving in different direction. We have V1 initial, V2 initial. So V1 initial and V2 initial are the initial velocity of the object. And V1 final and V2 final are the final velocity of the object. Okay, so here, if our M2 is at rest, then for completely inelastic collision, we are going to have M2 at rest that goes to 0, then M1, V1 initial, they are going to stay together after the collision, and it will be equal to M1 plus M2 times V. So they have the same velocity. V1 final, V2 final have the same velocity, which is the big V here. Okay. So we have a general setup for incomplete elastic collision, M1, M2, and then M1, M2, initial, final, and then initial 0, and then stay together. So different cases have different join, but we all apply to this equation here. Okay, and the center of mass velocity remains unchanged if there is no external force applied to it. Okay. And then you can take a look at this picture here. So this shows a freeze frame of a completely inelastic collision showing the center of mass velocity. So you can see we have M1, M2. So the center of mass is like here, velocity, and when M1 hit M2, so M2 is 0, M1 hit M2, this is collision happens. So center of mass is moving with M1. You can see center of mass moving along here. And then when they are staying together, they are moving together. So center of mass also moves. Okay. So say this line here shows you the location of the center of mass during the collision process. And the VCOM stays constant. So this is that. So we have the checkpoint here. Body 1 and body 2 are in a completely inelastic one-dimensional collision. So what is their final momentum if their initial momentums are 10, 0, 10, 4, and -4? This is very simple, okay? You just add these two values because the momentum is conserved. So 10 plus 0 is 10. So the first answer is 10. 10 plus 4 is 14. So 14. And 10 minus 4 is 6. So 6. Okay. And we also have elastic collision in one dimension. What is elastic collision? It's the total energy is conserved. Okay. So there's no kinetic energy change. In an elastic collision, the kinetic energy of each of the colliding body may change, but the total kinetic energy of the system does not change. So for a stationary target, conservation law gives M1V1 initial will be equal to M1V1 final plus M2V2 final. A stationary target, that means your M1 plus M2, V2 initial is 0. So you only have M1, V1 initial here. And then we also have conservation of energy. So remember the energy equation? See, this is the kinetic energy before, and these are the kinetic energy after. Okay. And this is the generic setup for an elastic collision with a stationary target. So this guy hit this guy, and these two have the final velocities. And with some algebra, we can calculate the final velocity, because take a look at this equation. If we know V1 initial, then know the masses, then V1 final, V2 final are the variable we have to solve. We have two equation, two variable. We can try to solve the final velocities. So some algebra, and we can get our final velocity here. And we have some very specific result. Like if we have equal masses, then V2 final equal to V1 initial is the first object stops. And if we have massive target, then the object just bounces back, speed mostly unchanged. And we have massive projectile, M1 is very large. Then M1 V1 final will be equal to V1 initial, and M2 final will be equal to 2V1 initial. Okay, it's the first object keeps going at almost the same as initial speed, but your final velocity of M2 doubled. Okay? So this is this. And if we also have both of the object moving after some algebra, you are going to get this. You can do the calculation of the derivation by yourself, but we have the equation here. It's very simple. You just use these two equation here, do some algebra, you will be able to get the final velocity. Okay. And here we have a generic setup for an elastic collision, and we can have these two, and then kinetic energy is conserved. So with equal masses for elastic collision, so if the m1 equals to m2, what will happen is they are going to exchange their initial speed. Okay. So we take a look at this checkpoint here. What is the final linear momentum of target in line 18, which is this guy here? If the initial linear momentum of the projectile is 6 kilogram meters per second, and the final linear momentum of the projectile is 2. So here, if 6 is the initial, if 6 initial, and then if 2 to the final, and then you have 4 left, right? So the other object will gain momentum, which is 4 kilogram times meters per second. So this is 4. And B, -2, -2, you should have 6 minus -2, and you are going to get 8. And what is the final kinetic energy of the target if the kinetic initial and final kinetic energy of the projectile is 5 and 2? So energy is conserved. 5 will be equals to 2 plus K2 final. So K2 final will be 3 joules. So they are very easy. You just need to understand what is happening for the collisions. Okay. And also we have collision in 2 dimension. Yeah, let's quickly go over that. This chapter is a little bit long, okay? So collision in 2 dimensions. For collision in 2 dimensions, we have to apply the conservation of momentum in each axis, okay? And if we have elastic collision, then we apply the conservation of the energy. So take a look at these 2 equations, okay? We are going to have conservation of momentum, and the conservation of the energy. Okay, so you see the cosine theta, sine theta, and sine theta here. That is, after the collision, you have to find your x and y component of your V2. So V2 final x is here. That you are going to get the cosine, and the final y, you are going to get sine. Okay, so that's why you can see y is sine and x is cosine, and the conservation of the energy will not change. Okay, problem like this can be very difficult to calculate because we have a lot of trig functions. So be very careful with collision in 2 dimensions. Okay. And here, so the previous equations, 3 equations, for a stationary target have 7 unknown variables. So if we know 4, then we can solve for the remaining ones. So these are very difficult to solve. Okay, so let's take a look at this checkpoint. Suppose that projectile has an initial momentum of 6 and a final x momentum of 4 and a final y momentum of -3. Okay, so initial we have 4. Oh, we have 6. And then this is 6, the 6 is 4x, okay? And then we have 4, oh, I shouldn't do it this way. 4 is for x. So this is 4 for x, and this is 1. And then you are going to, and we also have -3 for y, okay? Y, 1. And you are going to calculate the final x component of momentum and the final y component of the target. So you should have initial 6 will be equal to 4 plus p2. And then this is for x direction, right? X is 6, 4, and then y initial is 0, and then it equals to -3 plus p3y. So you are going to get 2 for p2x. So the equation, and you are going to 3 for p2y. Oh, why write p3y? It should be the momentum for the second object, for the target for y direction. Okay. And then we have system with very mass. This is not covered for our exam. So we don't have, because it involves relative velocity, so we are not going to do this section. So only section 9 to 8 is on our exam 3. Okay, it's not on exam 2. Exam 2 covers chapter 5 to 8. And we can skip that. So this chapter is a little bit long. We talked about the center of mass, and we also talked about conservation of momentum. For this equation here, be very careful. Our velocity is vector. Okay, so you may want to be very careful with the signs for your velocity. And collision, elastic collision. And that will be all. Okay. So that is chapter 9. Okay, so that will be the end of the lecture today. Thank you, Marissa, for staying with me the whole time. Okay, so I'm going to stop here. Tomorrow is a national holiday, so we do not have any class, but I will post the exam on D2L, okay? Thursday, make sure you finish the exam on time. And Friday, we still have lecture, okay? So bye-bye.